All right. Hello, everyone. So on behalf of American Membrane Technology Association and Toray Membrane USA, I'd like to welcome you all to today's webinar. Achieving high silica, boron, and urea rejection with brackish RO membranes, advanced solutions for the ultra-pure water market and beyond. My name is Sean Carter. I will be moderating the webinar today. On our webinar today that is hosted by Elke and Toray will be one presentation presented by Ramiro Ramirez and Elke Peirtsegaele and myself. Following the presentation, there will be a question and answer session if you have some questions that you'd like to ask. I'd like to go over a few housekeeping items before our first presentation. First, all participants are muted for the webinar. If you would like to switch your audio from your computer to your phone, use the control panel in the upper right-hand corner of your screen, select telephone in the audio panel, and the dial-in information will be displayed. As mentioned, you will have the opportunity to submit text questions at any time during the presentations. Select questions from the drop-down menu towards the bottom of the control panel. Questions will be collected and addressed during the Q&A session at the end of the webinar. You can download today's presentation by clicking handouts in your control panel and saving the PDF file to your computer. Lastly, at the conclusion of today's event, a survey will be displayed. Please take a moment to complete our survey, and we encourage your engagement and welcome any feedback. And at the conclusion of today's event, I already mentioned that we can encourage your feedback. So let's get started. So I'd like to introduce Ramiro. Ramiro Ramirez is a chemical engineer with a degree from University of California, Santa Barbara, and over a decade of international experience in the water industry. His professional background spans a wide range of roles, including hands-on operation, O&M contract and sales of systems, and technical support and sales for specialty chemicals and membrane technologies. His blend of technical and commercial experience enables him to work effectively across diverse markets and project types to deliver results-driven solutions. Ramiro currently manages Toray Membrane USA's commercial efforts in Latin America and the Caribbean, bringing a well-rounded, regionally informed perspective to the water treatment challenges with a focus on customer success. And for Elke is a regional sales manager for Toray. She covers Western United States and Canada. She has over 11 years of experience in the membrane industry with a deep expertise in reverse osmosis, nanofiltration, and ultrafiltration technologies. Elke has held various technical and commercial roles and uses her experience and passion to help customers find solutions to their water treatment needs. All right, so we're going to go ahead and get started with our slides here. And like I say, as you have questions, you could type them into the questions. We'll go through them at the end and answer as many as we can. So I'll briefly introduce Toray. Toray is typically not a household name in the United States, but it is a household name in many countries around the world, depending on the marketing efforts there. There is a wide range of Toray products that we provide, not just in the water treatment segment, but in many other segments as well. So Toray is, in essence, a materials company, right? With the slogan, materials change our lives, which originally, Toray started as Toyo Rayon in the 1920s. We'll be celebrating our 100-year anniversary next year. But originally started as Toyo Rayon, which was a Japanese rayon company. And since then have evolved into many, many other markets in many business segments. The Toray's largest product globally is carbon fiber, but we are in many things that you might touch on a day-to-day basis. The aluminized foil in snack bags is a Toray product that you've probably handled lately. And many clothing articles that many of you have at home are probably made by, or the original textile is actually made by Toray. So, but Toray's goal has been to provide products that help build a more sustainable world. So we do that by contributing to communities and, of course, advancing materials for the future. So by providing these much more updated materials, we can make our communities more efficient, healthier, safer. But today we're specifically going to talk about membranes. That's what everyone's here for. So we specifically will want to highlight reverse osmosis products, specifically our new line of TBW membranes. We're also going to talk about our newest projection software, which is AquaGrid. And we do have new products in the ultrafiltration space. Our fine, ultrafine UF that we've launched just this year. Also our integrated rack solution called our Tough Rack. However, we won't be presenting on those today, but if you are interested in any of those UF products, please reach out to us and we'll be happy to discuss those with any of you separately. For today, we'll focus on reverse osmosis topics. And with that, I'm going to pass it off to Elke to talk about some of the technologies that we've been working on.
Awesome. Thanks, Sean. So yeah, as Sean mentioned, we're going to be primarily focusing on RO membranes today and the development that we've made in the technology here at Toray. So just to kick things off, I think it makes sense to, show what a traditional polyamide RO membrane looks like. So here on the screen, we have a cross-sectional SEM image of a polyamide RO membrane. So you can see the 3 layers in the membrane. So at the very top, you can see this very thin layer, and that is the cross-linked aromatic polyamide chemistry. And so that layer is actually referred to as the barrier layer or the separation functional layer. And essentially, it is responsible for rejecting the dissolved solids that are present in a feed water. So that is the membrane that is doing the rejecting. That sits on a polysulfone support layer or inner layer. And that polysulfone layer is microporous and essentially serves as a support layer for that thin polyamide layer up at the top. And then that sits on a non-woven polyester fabric, which is the thickest of the 3 layers, and that is known as the substrate that the membrane is cast on. So that substrate basically provides the mechanical strength and durability for the membrane. So that's what a traditional membrane looks like. Now we'll kind of talk about the things that we're looking for in an RO membrane as they're used widely to treat surface waters, wastewaters, etc. So when it comes to RO, we're always looking for a membrane that has reduced energy consumption, right? We want to lower that OPEX. We want a membrane that produces high quality permeate, right? We want to meet those permeate quality requirements. We want a membrane that's anti-fouling, and then we also want a membrane that has high durability. So today we're going to focus on the first 2 here. We're going to look at how can we reduce the energy consumption of a membrane. So in order to do that, we need to have a membrane that has higher flux or higher water permeability. And one of the things that we can look at in the membrane chemistry to achieve higher flux is looking at the protuberance structure. And we'll get into that, so don't worry about that just yet. And then when we're looking at creating a high quality water permeate stream, we want to create a membrane with higher rejection, right? So in order to achieve that higher rejection, we want to look at the pore structure within the membrane chemistry. So we're going to dive into those in a little bit more detail here. So as I mentioned, we're looking for a membrane that has both high salt rejection characteristics as well as high water permeability, right? So in this graph, we're striving for this magic corner up in the top right right? So we want a membrane that has high rejection, high flow. Traditionally, we've had to do a balancing between the two characteristics, right? So typically when you have a membrane that has higher salt rejection, that permeate flow kind of drops off. And then vice versa is also true. When you have a low energy membrane, that permeate flow is higher, but that rejection comes down a bit. And so that's represented by this blue diagonal line here. So we're striving to get to this magic corner. So how do we do that? So on the right-hand side, we have a diagram that kind of shows you the theoretical concept behind the membrane, right? So on the left-hand side is what a membrane looks like today, an RO membrane. So these black lines represent the polymer chains, and you can see that there's cross-linking there, but then there's also some imperfections within that chemistry, and that creates these voids or pores. For those charged ions that are present in the feed water, those get rejected pretty well by an RO membrane because that polyamide surface typically has that negative charge. But for neutral molecules like boron, silica, urea, those can pass through some of these voids. So in order to improve the rejection of those neutral molecules, we need to look at that polymer cross-linking, improve that, create more uniform, smaller pores to remove those voids. So that's what's being depicted on the right here. Another thing that we need to look at is how does the structure of the membrane surface itself lead to water permeability? So we'll look at that as well. So going back to this SEM image that we showed at the beginning of the presentation, we're going to zoom in on that polyamide layer and see what we can do to get closer to developing a membrane with higher rejection as well as higher flow. So if we take an SEM image of the surface of the membrane, so this is us looking down at the surface of the polyamide membrane, you can see there's a lot of these, they look like bubbles, right? So these are the peaks and valleys of the surface of a polyamide membrane. And each one of those peaks is known as a protuberance. So there's that word that we saw earlier. And so what we can look at as well is take a cross section of those protuberant structures, and we can see, again, the surface of the membrane has these ups and downs, the peaks and valleys, and we're going to see what these structures, how they impact permeability as well as rejection. So by taking some TEM images, we can look closer at the protuberant structure, and we can actually take some measurements. We can look at the surface area of each of the protuberants. We can understand, okay, how much surface area is there at the membrane surface? And then we can also measure the thickness of this protuberance. So you can see it's a little bit thinner here at the top, and then it gets a little thicker here at the bottom. So not super uniform, right? And if we measure these two things, the surface area and the thickness, we can potentially see what impact that has on permeability through the membrane. And we can kind of see that relationship in this formula here. So again, here's kind of a diagram of that protuberance, and you can see that flux is proportional to surface area over thickness. So obviously, if we can increase that surface area at the membrane surface and reduce or make that the protuberance thickness more uniform, we can essentially increase that membrane flux. So that is exactly what we set out to do. So the first part was getting that data. So we have a bunch of really expensive microscopes that allow us to take all these really cool images. And you can see here on the left-hand side, we have a 3D image of this protuberance, and it allows us to measure the surface area. It allows us to look at the thickness of the walls of that peak. And you can see here, this thickness isn't uniform, right? You've got a thinner wall here, but it's thicker over here. that can lend to discrepancies in flux when looking at that specific protuberance structure. So by taking all these measurements, we actually realized, like, yes, the surface area and the thickness of these structures does correlate to membrane flux. So now it comes to, how do we tailor that structure so that we can achieve that higher membrane flux? So here on the left-hand side is an image of a conventional membrane, and you can see that protuberance height, right, on average. With the new membrane chemistry that we've been developing or have developed, you can see that protuberance height is much greater. And obviously, by increasing that height of these structures, we are thereby increasing the surface area of the membrane. And as we saw in that formula, if we can increase the surface area, we can also increase the permeability through the membrane. Another thing is looking at the thickness of each of those protuberant structures. So as you can see, the conventional is in purple here, and you can see the distribution of thickness is quite wide. There's a lot of variance in the wall thickness of those structures. And if we can hone in and kind of collapse or get more refined on that distribution of thickness, we can get a more uniform structure, and that will also help us increase the flux through the membrane. So that is exactly what we've done. And then, we've talked about the permeability of the membrane and improving that, but we also need to talk about, how do you improve rejection, specifically of these neutral molecules that slip through these voids in the polymer chain or the cross-linking, right? So again, an SEM image of a conventional RO membrane. This is protuberance, and then here on the right-hand side, we're looking at the actual polymer chains in the polyamide chemistry. So this is actually really cool. The white image is the actual polymer chains within the polyamide membrane. And then the darker portions in this image are those voids, or those imperfections in the cross-linking, or what you can call a pore, right? So that's where those neutral molecules like boron, silica, urea, those molecules will pass through those voids. So how can we improve this? How can we essentially ensure that those voids are gone? We can improve the cross-linking. So if we improve the cross-linking to create that uniform, small pores throughout the surface of the membrane, we can reduce the amount of large pores that are present, and that will obviously improve the rejection of those neutral molecules. So on the right-hand side here, we have a graph that kind of shows you the pore size distribution for an NF membrane in gray. So you can see that's quite wide. And then you've got the conventional membrane in blue. Again, not as wide as the NF membrane as probably expected, but there's still quite a large distribution of pore size there. And then you've got the red, which is the new RO membrane chemistry that we've developed here. And you can see that pore size distribution is much more narrowed in, and that helps, again, reduce those larger pores for passage of those neutral molecules. So then just to kind of show you a side-by-side image here, again, we have that SEM image of the conventional membrane that I showed you earlier. Again, the white being the polymer chains and the black being the voids. And so you can see this is not very uniform. You've got a wide pore distribution here. But if you compare that to the new membrane that we've developed, you can see that we've really improved the cross-linking here. And you see it looks much more uniform throughout. You don't see as many of those bigger pores. So this allows us to retain the rejection of those charged ions, but then also increase the rejection of those neutral molecules, which is very important. So Again, these images are really, really cool. They're done by these extremely expensive microscopes that we've invested in so that we can do this development work, which is pretty neat. But so now that we've kind of talked about the developments in the membrane chemistry and the improvements, I'm now going to pass it on to Ramiro to explain why this membrane is so important and the various applications that it can be used in. So Ramiro, over to you.
Yeah, thank you for that. The detailed explanation of the technology, and I want everyone on the call to kind of keep that in mind. We're going to talk about the real life application and introduce the TBW membrane, but just keep in mind that that comes through a lot of efforts and actual improvements in the technology as described by Elke. So what's the importance, right? What's the sense of urgency in improving the technology? And that's because the market demands it, right? For us, we've had improvements over the years in the removal of dissolved ions, something that we do very successfully, but the passage of neutral molecules is ever pressing with water scarcity and just in the spirit of optimizing technologies. It's incredibly important. So, some of the most common neutral molecules that we're going to be discussing and that we see the need for efficient removal are silica, boron, urea, and PFAS, which I'll explain towards the end of the presentation. So one of the origin stories, so to speak, for this new membrane is the ultra pure water market. So semiconductors, we all use them, right? That they've become sort of a core product of society today, and it's a very, very high efficiency process. If anyone here has ever been to one of these facilities, you'll be amazed by the level of detail and the redundancy they require to basically achieve the most pure water possible, right? That's what they're trying to achieve. So they're stretching really the theoretical limits for ultra pure water, right? In that process, typically you'll see a combination of technologies, one of which would be reverse osmosis in single pass and oftentimes double pass, right? So for these facilities, any silica present is a huge risk, right? So the removal of silica is incredibly important. Silica is a neutral molecule, so it has an easier time historically passing its way through the reverse osmosis membrane. So in these types of applications, anyone dealing with any ultra pure application where silica is incredibly important will want to consider the use of this new membrane technology, and we can model that with information, right? So the same way we've been able to model silica passage, we can do that with the new technology. That's not to say that ultra pure water spaces is the only market. These are applicable. Just pulling water out of the ground. I work a lot of projects in Latin America where oftentimes the silica concentration in certain regions of Mexico and Peru are approaching 50, 60 ppm in the feet. So this is a limiting factor not only in terms of scaling, right, but in terms of the quality that you're trying to achieve. So if you're in any applications that you're perhaps struggling with the concentration of silica in the permeate, give us a call. We'd love to model that with the membranes. And then seawater, right? So boron is a very, very tricky constituent to reject, right? And oftentimes we have to use a second pass. We have to modify the pH to sort of play with the charge of the boron in an efforts to better remove it. So these seawater plants are massive. They require tons of capital investment, tons of energy to operate. So any room for improvement with respect to boron rejection is something that we're going to want to consider heavily. I'll just give one example again and kind of just double down on why it's so important to monitor for some of these, in particular silica. So in the bulk of my career, I spent a lot of time in the power generation space, and these steam turbines are incredibly expensive and really sophisticated, very sophisticated design. Each of these blades is engineered precisely and balanced to produce energy, right? Any imperfection, any pitting, scaling on any of these blades is going to cause tremendous inefficiency. So Oftentimes, these high-pressure steam turbines are monitoring for silica consistently and trying to achieve levels below 5 to 10 parts per billion. Typically, you have an RO system, right? That's going to be doing a bulk of the work, and then you would pass that through some kind of polishing step, whether that be a resin, inlaid lag, EDI or CDI technologies, and extending the regen frequency is really important, right? So these resin systems, for example, will typically break through on silica. So they'll monitor the conductivity, they'll monitor the silica, and silica as it's easier to pass through RO, it's actually easier to pass through resin as well. So oftentimes they'll be monitoring the concentration of silica, and when they reach a certain level, 5 to 10 parts per billion is when they'll have to trigger a regen. So the more we can take out with the RO, the more not only risk you're managing, but you're also going to get that sort of investment back in reduced regen requirements. Here in California, we're seeing a lot of off-site regen and ZLD applications. So the more you can optimize this, the more commercial benefit you're going to see. So again, just keep that in mind if you're in any of these coal plants, these HRSG heat recovery steam generation plants. You're going to want to consider the best membranes possible for the removal of silica. And again, just kind of some general facts here. From my time in the space, even a 1% efficiency loss on a 100 megawatt plant can result in losses of well over $1 or $2 million per year. Just 1/16, a very small layer of silica can increase your fuel consumption by 15% in these spaces. So silica, these operators live and breathe by that value. So let's give them the best chance we can, right? Not only the quality of the water that you're producing is important, but also the quality of the water that you're taking in, right? So if we look at this chart here on the left, we kind of have a general breakdown of how we use water on a global scale, right? So we use a ton of water in the agricultural space. We use it for industrial, and obviously all of us use it for domestic. And with increased population, increased manufacturing, we're going to be in a position where we're going to face water scarcity challenges, right? Pulling out of rivers, groundwater, and seawater. We want to make sure that's sustainable. So to supplement that, as I'm sure many of you have seen, are projects of wastewater reuse, right? So we have access to that water supply. Can we treat it? Absolutely. But is it more difficult to treat than a well? That is also true, right? So in applications where we're reusing wastewater, typically we're going to see concentrations of TOC and urea in that stream be, orders of magnitude at times higher than water that we may have been used to treating. So urea is another constituent of concern. You can get it from natural processes, from agricultural runoff. It can sort of leach into the groundwater, and the molecule itself, again, is neutral, and it's very small in diameter. So it's it's not that much larger than water. So as Elke was explaining, any imperfections or sort of gaps in the cross-linking are opportunities for that urea to come in. So we want to make sure that we're optimized to remove as much urea as possible, which again is another constituent of concern, especially these days as we're approaching more and more water reuse projects. So again, we just want to reiterate sort of the need and sort of the urgency to optimize that system. So the technology that Elke explained at the beginning of the presentation has a name. So that is the new TBW series. So this is we're very excited as a company to be releasing these products. These products are officially available for release, so you can contact myself, Elke, Sean, or your local Toray rep, and we're happy to provide you information on the membrane. You can download these data sheets on our website. So if we kind of just take a closer look, we have two membranes available in that product category. We have the one on the left, which is the TBW HR, and then we have the one on the right, TBW XHR. I'll explain the differences here in a bit. But these are available in 400 and 440 square foot versions. The one on the left, you'll kind of see the test conditions resemble more in the field of a brackish, a low energy brackish membrane. And the one on the right, we're at a test condition there of 290 PSI. for single element wet tests. So we're going to be, a little bit elevated, sort of not quite in between a brackish and a seawater, but certainly sort of filling that space. So again, when it comes to membrane selection, we're going to want to play the game. Are we trying to take advantage of a low energy or a high rejection, and we can kind of balance that case by case to figure out if the HR or the XHR is a more appropriate membrane for that particular job. So for anyone here on the call who's perhaps worked in the membrane space, you may have seen a chart like this. And this is a chart showing the difference of the A and B values. So there's a lot to go over here. I'll kind of, we'll take it a little here step by step. But just as a refresher, the A value, which is plotted on the x-axis, is the water mass transfer coefficient. So this is just defining the rate of water transferred through the membrane. And generally speaking, you want a high A value. So this is, towards the right of that graph. That means that you're able to achieve a specific water flux at a lower operating pressure. Plotted on the y-axis, you have the V value, which is the salt mass transfer coefficient, and this is the rate of salt diffusion through the membrane. And again, generally speaking, the further you go down on that graph, the better salt rejection you're going to achieve. So in a perfect world, you're going to, generate a membrane that's at the bottom and the right side of that graph. So we have 4 elements plotted here. If we kind of just focus on the 2 on the right there, so the element plotted in that orange line is the TBW 400HR, which again is at those lower pressure conditions. And then right next to that in the gray is the TM720D 400. For some of you that are familiar with the Toray membrane nomenclature, that's our high rejection brackish element, which has been a flagship element for Toray, something that we're very proud of and has thousands of successful applications worldwide. So you can see there, there's a little bit of overlap, but generally what we're presenting is an element that can sustain higher rejection at low pressures, right? So that's something that we're demonstrating here and something that's a huge advantage. And we'll kind of go through that in a little bit more detail here in the coming slides. And the one on the left, the 2 sets there in the yellow, you'll see the TM820V 400, which is a low energy seawater membrane. And then just to the right of that, you'll see plotted in blue the TBW 400 XHR, which again is a new membrane in the series, making use of the technology that Elke explained. And you'll kind of see the difference here. You'll notice they sort of look similar in shape. But the one in blue there, the TBW XHR, is a little further to the right than the seawater. So what we're trying to demonstrate here is that you're effectively able to achieve those types of rejection values that you may have become accustomed to in seawater at much lower pressures, which is significant, right? Operating a seawater system or seawater membrane, you're going to have to make a lot of adjustments. You're going to have to invest more into the energy. So to be able to achieve what you're trying to achieve with the seawater membrane at lower conditions is significant. So when you're doing modeling, when you're doing projections, it's important to do your energy balance and consideration, right? Because the cost savings in switching membranes here could be considerable and something that shouldn't be overlooked, right? So if we kind of take a look at the published information, to no surprise, the collective efforts of the Toray R&D team have paid off, right? So looking at this here, we're just looking at a conventional membrane, the boron rejection of a conventional membrane, as opposed to the new ones that we're generating, right? So this one here is specific to boron. The test conditions in this particular example are a little bit different than the ones published on the data sheet, so we can kind of go through those details on a case by case with your local Toray rep. But the difference of 5% here in this particular example is, it may not seem like quite a bit, but at this point we're talking orders of magnitude difference of what you're projecting in your permeate. So depending case by case in certain areas where you may have been expected to do a double pass system or get creative, we are kind of opening the door to potentially getting away with a single pass or maybe not dosing as much caustic in the second pass. There's a lot of different sort of groups here that we can explore case by case, that we can sort of open up with these new membranes. Just following this trend here, looking at a couple different examples. So here on the left, you can see the difference in salt rejection, a conventional membrane in the blue line versus what we're able to achieve with the new series of membranes. On the right, we're seeing a silica rejection value. So for the XHR, a nominal rejection for silica is 99.9%, which is significant. Like I said, it may not seem like a big leap from 99.7, but when you actually pencil out the calculations and take a look at your projections, the improvements are notable and exciting. Just kind of going through a couple other ones here. So we talked about boron and urea and how difficult they are to remove for the size of the molecule and for the fact that it's neutral. So again, this is just to demonstrate the data that we've acquired with these new membranes and how they compare to what we're used to seeing on the conventional side. Again, just wrapping up a couple of those here. So acetone and IPA. So, acetone is not something you likely want to introduce in our system, but it's a good indication and sort of what we use as a benchmark for, the removal efficiency of neutral molecules at varying molecular weights and molecular sizes. So again, the trend we're seeing here is improvement across the board. It can vary depending on which constituent you're trying to remove, but again, Elke's explanation is so important because it's providing a technical background as to why we're seeing these new values and really an explanation as to how we're able to achieve these improved rejections. One other important thing that we want to chat about here is PFAS as well. So PFAS, I'm sure everyone here on the call to this point has come across the term. Can you go back just 2 slides? 1 second here. Just want to go back. There we go. So PFAS is per and polyfluoroalkyl substances. PFAS is sort of the blanket term. Many of you might know them as forever chemicals. These are chemicals that have been in production, since the 1940s. We've all taken advantage of these chemicals through, nonstick, pans, the materials to make your clothes waterproof. They've been used in military applications across the board. And, as of the past couple of years, we're sort of, unfortunately, coming to terms with the fact that these are persistent and have been linked to, a wide array of health consequences for humans, right? So again, these are to say that they're constituent of concern is sort of old news. We've been sort of struggling with the removal of these. It's kind of tricky, right? Because it's not sort of a blanket one size fits all. There's different families. If you see in this diagram, based on the level or the amount of carbon chains, they can vary in length. There's the PFOS, which has typically a carboxylic acid, a sulfonic acid functional group. And you'll see the ones on the bottom, PFOA, which use carbon chains, and then they'll have a carboxylic acid group. So they'll vary based on size. The functional groups, the surface charge are different based on which one you're looking at. So, the removal of these has been historically challenging. I kind of just again a little bit more background on PFAS. They make use of a carbon fluoride chain, which is the strongest chain in organic chemistry. So to be able to just destroy them in water or degrade them is not particularly trivial. They're incredibly difficult to break down. So for us, and our tactic is to effectively use reverse osmosis to concentrate that, minimize, put that all in a bucket, and then deal with that concentrated solution more effectively. Again, For us, historically, it's been very challenging. We've been approached many times over the years asking for, removal efficacy of PFAS, and it's not so easy, right? Because it's not just one chemical. If you look at short chain, which is typically 7 carbons or less, or long chain, which is typically 7 carbons or more, there's cyclic, there's branched constituents. So if you kind of move those puzzle pieces around, you're generating over 15,000 unique chemicals, all with different charges, all with different sizes. Really that uniformity that we're able to achieve in the TBW series is going to be able to more effectively, non-selectively remove these constituents from a water source. Again, if we kind of just take a look at the different categories of chemicals here, we'll notice that they're all of different molecular weights. So again, with us being able to produce a membrane that is more consistently the level of cross-linking, better at rejecting PFAS components of all molecular sizes, we're able to more confidently, more accurately, and more efficiently remove sort of this, families of products. Taking a look at this map here, again, I wish there was sort of an escape, but at this point, we're seeing that these have become pretty ubiquitous where areas where humans reside. So I'm sure many of you have been involved in certain projects, and we can certainly expect to see many projects across the United States which are going to require removal of those PFAS components, right? So I won't spend too much time on here. We could easily spend, a whole webinar talking about the intricacies of PFAS regulations and PFAS removal. But needless to say that, the EPA has released these guidelines. We're talking, again, part per trillion levels at this point. There's our requirements to monitor and test for PFAS in, potable water sources. And any sites that are seeing, certain concentrations, elevated levels of PFAS are going to be required to incorporate some kind of technology to get these below the MCLs, and those timelines have been established. So, the time is now. It's not something that we're speculating at this point. There are, actual regulations that have taken place. So we can expect to see these products come to fruition here in the coming months and years. As far as technologies that we have to deal with PFAS, right? We have granular activated carbon, GAC, we have ion exchange, and we have reverse osmosis are 3 common ones. So each of them, in my opinion, has a pro and a con, depending on what type of water you're trying to achieve, the flow rates. Do you have long chain? Do you have short chain? You might use any one of these technologies or any combination of these technologies. GAC is typically, pretty effective at large flow rates, but it might be challenging to dispose of it once you saturate it with PFAS. It's also, effective at removal of certain chain sizes more than others. Ion exchange has a nice removal capacity, but it's an expensive product to produce. RO on our side, that's what we can speak to with a little bit more clarity, is very effective at both long and short chain removal. It was so before, and it is even more so now with the new technology, right? It has a compact footprint, no regeneration, but you do have to find a solution for the brine stream, the concentrate stream, right? That's historically been something that's been a little bit challenging if we look at a standard sort of UFRO system. Very effective at removal, very effective at concentrating, right? So if you're operating at a very high recovery, you can sort of funnel all that PFAS and concentrate it down to as concentrated as a reject stream as you can achieve. But the question remains what to do with that stream, right? So again, this is a very, very high level overview. We can, if any of you have any specific projects or want to talk about these concepts in more detail, we're happy to, but there are, a myriad of different technologies that we can utilize to dispose of that, so that historically been a challenge, but again, we do have avenues for that, and making use of a TBW style membrane, you're going to be able to further improve the concentration of that and generally just optimize your system. So the last thing I wanted to touch on here before we end the webinar is our AquaGrid software. So this is our new version of the Toray membrane production software, which is available to download now. So this has been, years in development. We're excited to have this released. For anyone here that is familiar with the Toray product line, you may have used the DS2 software in the past. Very, phenomenal software, but as you may have noticed, a little bit sort of antiquated in its user interface. So we've upgraded that. I would encourage everybody on the call here to download it and reach out to myself or Elke or your Toray rep. There's a lot of really interesting tools. You can do batch calculations, so you can do multiple iterations of a design in the same projection. You can do your min and max temperature all on the same projection, so it's going to save you quite a bit of time. For me, it's kind of similar to sort of an Aspen HYSYS software if you've used that in the past. So you have the ability to basically design the RO system, and you can make use of incredibly complex models. So you can do, one RO feeding, a second pass, partial, recycling, sacrificial, or concentrator RO. You can do all of that in the same design. You can do multiple iterations of that. So it's, anyone here who's done those complex designs, sometimes you have a folder with 30, 40 projections on it. So we've taken steps to simplify that. So definitely download this and have a look. We've added we've incorporated the ability to model on NF, and this is just a start. So over time, keep an eye out for new updates and new releases. We have some new developments coming to the AquaGrid software, which are pretty exciting. So again, download the software, play around with it. This software comes from many years and decades of sort of research and development. Empirical values experience. So there's a lot of information packed in there, a lot to see. Like I said, you can always reach out to myself to set up a training and go over all the features. If you guys have any projection requests, go ahead and reach out to your Toray rep, provide the information. We're always available to review projects case by case and make sure we're optimizing and making you aware of what membrane technologies that we have. A lot of what we talked about today, right? PFAS, boron, urea, silica. Boron and silica, you'll find those values there in the software. PFAS is a little bit more challenging, but we do have, sort of a database of real data that we've been working very hard to collect. And it's not publicly available, but you can always reach out to us with any of those projects, and we're happy to provide you more detailed technical response and projections. To now we have higher degree of confidence and better modeling tools for those types of projects. So again, please keep that in mind. And with that, I'll go ahead and thank you all for your time. Again, Sean, Ramiro, myself, and Elke, appreciate you guys joining the webinar. We went through a lot of information there, but you're always welcome to reach out to us directly. We're happy to discuss any of this here in more detail. So with that, I'll loop it back to Sean and see if we have any questions from the group.
Yeah, great job, Ramiro. Thank you. Elke, thank you for your presentation as well. A couple of questions that we've got that came in, if we do not answer your question on the webinar, please note that I will be distributing these questions to our team for follow-up. So if we don't get to your question within the webinar, perhaps there's some confidential information in the answer to the question or something of that sort, we'll reach out to you individually. And all the questions we're getting, we do have your name and we have your contact info, so we can follow up with you there as well. But first question for you, Ramiro. Someone asked, can AquaGrid demonstrate the PFAS rejections for projects?
Yeah, and the short answer, so if you were to download the software, you wouldn't see the ability to enter it like you would enter silica or calcium. But we have been, like I said, working very hard doing lab scale tests. So we do have data on our site internally. We'd encourage you to reach out to us directly. There's a little bit more complexity that we'll want to review case by case, but yeah, I mean, this is an important constituent, one we've had a lot of demand for, and yeah, we've been working diligently, our team, to sort of start to develop a database and real data that we can share with you on a case by case basis. So yeah, I'm not sure who the question came from, but you can reach out to anyone here. The QR code has your regional rep as well. So yeah, if you have a particular project in mind, go ahead and schedule some time with us individually. We can go through the details. As you know, the rejection will ultimately depend on a wide number of factors. So we want to make sure that we're doing it effectively. We don't want to just give you oh, it'll do 95% right. We want to dig into the technical aspect of what you're trying to achieve and play around with those values to ultimately meet the goal that you're trying to make. So the short answer is yes, but talk to us directly.
Great, thank you, Ramiro. Let me grab another one here. There's a bunch of questions coming in and it moves the questions when I go to read it. So someone asked specifically about the removal of urea. And Ramiro, I believe, did you have a slide on that? And I don't know if you want to
Sure.
briefly mention that.
Yeah, absolutely. So if we go back, we'll kind of look at the data. Again, this will depend. It'll depend on the water. It'll depend on the operating flux. It'll depend on the recovery. It'll depend. There's a number of factors. So this, just kind of take this not with a grain of salt, but just understand the values being reported here are for single wet test conditions, which are defined below. But you can see, for a single element wet test on a conventional membrane, I use that term conventional sort of very loosely, but in a range of in the 70s, right, low to mid 70s, we're expecting upwards of 85 or higher, again on a single element wet test. So I'd encourage you to if you have a specific project where you're trying to achieve urea rejection through RO, go ahead and reach out to us, and we can kind of do the math based on what we're trying to, flow rates, like I said. We can play around with membrane selection and those operating parameters in an engineering scope to make sure that you understand, what we're projecting for that particular project.
Okay, thank you. One question that came in that I can answer as the moderator here, asking if we will be sharing the presentation, and you will be able to access this webinar later if you missed parts of it. You will be given I believe it's a link later that you will be able to go back and access this. And then next question, and Ramiro, you sort of touched on this, but this customer asked, is there online training available on using the Toray AquaGrid software?
Yes, so you'll actually, I believe, if you go to the, water.toray or just Google, Toray membranes AquaGrid, you will see some YouTube videos and some training videos. So there is a manual that you can go through, and there is, I think it's perhaps, 5 or 10 minutes video or so. So go ahead and take a look at that. What I would encourage you is go ahead and download it, right? And just sort of play around with it, spend, 20, 30 minutes. Just kind of familiarizing yourself with the interface, but I would highly recommend reaching out to your Toray rep. So I do these trainings very regularly. You can easily spend, honestly, multiple days going over anything from concepts of design, right? So if you want to go through sort of design concepts, That's a little bit separate from AquaGrid, but we can go through some examples and kind of let you know how we go about certain projects. If you're an expert in design and you just want to set aside some time to go through, basically the interface, how to do those batch calculation tools, because they're, like any software, right? Like Excel or PowerPoint or what have you, it takes some time to get familiar. There's a lot of sort of neat tricks that may not be completely apparent if you just open it. So go ahead and reach out to, like I said, you can reach out to myself, and if I'm not your primary, I'll put you in contact with whomever is. But the Toray team here outside is very technical. We all have a sort of an engineering background, and we have an applications team as well. So that's what I would recommend. We're more than happy to do that with you guys on an individual basis. We'll share links over time, so just keep an eye on sort of emails from the Toray group for sort of group webinars. But in my opinion, it's better to cater it individually based on your level of expertise with design and what you're trying to achieve. If it's more complete design course, or if it's just where to click to find the buttons, we can kind of tailor that to your specific needs.
I will add one thing to what Ramiro said too. I have had some customers say when they try and download the program, they have to bring in their IT team to allow for download. So just a heads up, if that's the case for you, make sure you have your IT crew handy so that you can actually download the program.
All right. And I got kind of a two-part question for you, Elke. First part is, for municipal projects involving boron, urea, or silica removal, do you apply a different design philosophy or membrane selection than you would for an ultra-pure application? And then sort of related to that question, are you going to expect to see a different scaling potential due to the higher rejection?
Good questions. So honestly, my answer for the first question of how you would change the design for a municipal versus an ultra pure project, ultimately it's always going to come down to what are the requirements that you're trying to meet and what is the feed stream coming in. That's really going to be the main driver of how you would design the system. So Ramiro kind of touched on this, whether you use the TBW or the TBW HR or the XHR is obviously going to depend on what you're looking for. And then for the second question as to whether you're going to see additional scaling, no, we don't expect any difference here, because scaling is, a function of those constituents that are becoming supersaturated. And so once they kind of hit that saturation level, they're going to precipitate. It's not going to be any different for this membrane versus another membrane.
And I'll chime in on that note as well, right? Say you're rejecting silica, and if you are rejecting more silica with a different membrane, could you hypothetically be passing a supersaturation limit? You could, but you'd need to look at the math of it, right? And part of the important part here is recognizing that on the concentration side, a little bit of difference in rejection doesn't mean a large difference in your concentration side. The biggest difference that you'll see is on your permeate side, right? And it's sort of the same argument that we look at a lot, right? When you're comparing the difference between rejection and salt passage, right? The difference between a membrane that's 99.8 and rejection and 99.7, which is the concentrates perspective, right? That's not a large difference. But if you're talking about the permeate side and you're talking about, well, 0.2% of salt passage versus 0.3, well, that's actually a very, very large difference, right? So you will notice in terms of percentage wise, a much larger difference on the permeate side than you're going to on the concentrate side. So hypothetically possible, and it will be important that we're working with our partners in the anti-scalant side to make sure that when you're running the anti-scalant projection, that it's correctly projecting how much will be in the concentrate. But we'd be happy to work with your chemical supplier using our projections to verify that you are still going to be not past saturation using a higher quality membrane like this. And then Elke, related to this question, another question came in. Well, okay, so that we were talking about scaling. Do you believe there might be any difference in fouling tendency with an increase in protuberance height?
That's a good question. I don't foresee any particular changes in fouling propensity with the increased height of the protuberance, but I will say that there are low fouling membranes. Toray has one as well, where we've basically created a coating, a hydrophilic coating that is covalently bonded to the polyamide membrane, and that essentially fills in any of those valleys in the surface of the membrane. And so that essentially allows for reducing the fouling of the membrane. So if fouling is a concern, that is a technology that is available as well to reduce the amount of organic foulants from sticking to the polyamide surface itself. And that is a permanent coating that's not going to wash off like some of the other technologies that are available today.
Okay. Thank you very much. I think everyone, that's all the time that we have for today. Thank you everyone for joining our webinar. And like I say, you may additionally reach out to anyone on our team. If you scan that QR code, it will take you to our OVU site, which will allow you to navigate to any one of us, and you can send us a personal message if you have a specific question for one of us specifically. And in addition, like I said, any questions that we didn't get to or didn't answer here, we'll be following up with via email after the webinar. But thank you everyone for coming and joining our webinar, and thank you to AMTA for helping us host this webinar. And we look forward to providing solutions to you all out there. So thank you very much for your time.
Thank you.
Thank you.